Hello, everyone. Thanks for taking the time to join us on this tech talk about mechanical seal support systems in water seal applications. And we really want to show you how SwitchLock can help with your mechanical support systems out in the field. The one note that I do want to make is if you could put questions in the chat, I'll try to answer them in order, more than likely at the end, unless there's something that I see that is relevant or upcoming, then I'll try to answer them at the time that you put them in, but more likely at the end, so you have at least 20 minutes to get that piece in. I am Ethan Liebswager. I'm our application engineer at Swagelock, Minnesota, North Dakota, and Appleton, and have been doing mechanical seal support systems for 4 to 5 years, and really wanted to focus in a little bit different on those that are using water seal plants, so the food industry, pulp and paper, because it's a little bit different strategy than what you may see out in oil and gas and refineries. Because oil and gas is more familiar with mechanical seal systems, I really wanted to focus with pulp and paper on a little bit more what a mechanical seal support system is and how to kind of identify it and how it can be advantageous to you out in industry. The first place that I always like to start, though, is looking at why are we talking seals? When you look at pump failures that are out there, between bearings and shaft shields, over half of your downtime is going to come from the failure of one of those two. And really, when you look at the repair costs, either the rolling bearings or especially the shaft seals will end up being about 2/3 of your repair costs, while also contributing to a large portion of your downtime that you may see out in the field. Again, I really want to give a good idea of where mechanical seals are used out in the field. So in any kind of pumping system, most people will be able to identify kind of where the motor is, your shaft, and essentially where your pump is. The one thing that kind of gets washed into the system is really where your sealing mechanism is. So when you go back to before the 90s, most of your seal systems were going to be some type of packing and or throat reducing. So that ends up being between the pump housing and the shaft seal, something to limit the pumped material from flowing back into ultimately our motor. As the technology has improved and gone to different methods, that's where you get into the mechanical seal. So instead of using an old pack seal where very typically it's either throat bearing or some type of rope packing, you can do the mechanical seal face. When you look at the mechanical seal, essentially you end up with essentially two faces, one along the drive line and one along the pump housing, that gives us our seal material. And again, it can look very washed into the system because your pump essentially is here. This back portion ends up being your mechanical seal section, and the front obviously ends up being your pump section. So in some cases, it can be actually very difficult to see right away until you really start to inspect the pump. When we look at a single face type mechanical seal, what ends up happening is, again, we have one section that rotates around with the shaft. So in this case, our shaft is right here, and we end up with everything in the black here that is actually rotating around with the shaft. So you get rigid static seals along this. And then we have a seal face that's part of the pump housing. So this is our pump housing here. Everything in red there actually stays stationary with the pump housing. And effectively our motive force, or really what we're trying to seal, is this seal face right here. Looking at it from a different angle, again, blue stays with the pump housing as a stationary, and then the rotating is yellow that goes along with the shaft, and we end up with kind of that seal face right there. And I'm going to show it a few different times to really get an appreciation for how tight of tolerances we're really working on. So again, the stationary and all of this piece would be typically O-ring sealed or metal sealed along with this and stays stationary, while this typically stays along with your shaft. You'll actually kind of notice this hole here. Typically there'd be some kind of spring force that's causing this to push up against our seal face, so that we're trying to minimize this as much as possible. And again, this is the part in red here that would actually be rotating with the shaft. What we want to do is we actually want to hydroplane this rotating face in yellow along the stationary face of the blue. So I kind of liken this to you're driving around on the highway stationary while your car is essentially some type of motive force, and you hit a patch of water and you end up hydroplaning across the road. No matter what you do in your car, whether you hit the brakes or anything, for the most part, there's no way to slow down because you've reduced your friction coefficient so much. Well, that's effectively what we're trying to do here. If you didn't have a fluid film and this is actually pushing straight up against our stationary face, imagine these pumps probably run anywhere from 500 RPM all the way up to 8,000 RPM, and you won't have much of a rotating face left. But by just simply hydroplaning some type of fluid film on fluid film, you'll end up reducing the wear to very typically in industry, we would target anywhere from 5 to 7 years before needing to replace this seal face. The fluid film ends up being the key area that we end up focusing on, because at Swagelok, we don't make any of the seals. We only support the service of them. So we really concentrate on that fluid film. Ideally, we want it as thin as possible. So typically we're talking 60 microns thick. You can imagine as I put more liquid into this, that liquid only eventually ends up leaking out. So if I end up putting gallons per minute across this fluid film, now I have gallons per minute that's actually flooding out and potentially can wreck our motor or bearings that would be sitting in the back here. That fluid film, again, is between the seal faces, ends up being, so the fluid film should be 2 micron thicks, and to put that in perspective, your human hair is actually 60 micron thicks. And again, too thin will cause wear, too thick we end up getting visible leakage. In the end, that's what we're trying to achieve, but there's a lot of things that we're really focused on. It must be present. Again, we don't want it to be dry running. That fluid film also has to be super stable. If we're going to be running 24/7, 365 at 5,000 RPMs, we can't have that fluid film even disappearing for a minute. A typical mechanical seal can easily burn up in a minute or two. So it has to be extremely stable. You can imagine that the fluid film can be either a gas or liquid, but the minute that we introduce solids, we end up having that abrasive force and not all that like to just not having it there at all. So it needs to be a very, very clean fluid. The other things that we're really looking at is, of course, the fluid has to be a reasonable viscosity for the application. We want it to be temperature controlled, because as you go up in higher temperature, you end up with much less, you get a lot more abrasiveness and essentially could evaporate our liquid, especially if you don't control that temperature. And then it also must be acceptable pressure for the pump conditions. And you'll see that a little bit more as we kind of go through this. So when, again, at Swagelok, we're really focusing in on that fluid film. So how do we create that fluid film? Depending on the mechanical seal, the media and application, you can end up with any potential one of these type applications. It can be simply just rerouting the fluid into our seal box. It can be provided externally in either a panel type form and or a seal pod type form, or in a worst case scenario with very specific medias, we can end up having an entire pump type system. When we look at water systems, the challenge is a little bit easier because for the most part, anything that we need to use for fluid film essentially turns into a water type system. And water is much more available than, say, out in the hydrocarbon world where we have very specific requirements. The other just kind of maintenance thing that I really want to touch on really quickly is what you'll see kind of throughout Swagelok's literature is the API terminology versus the ANSI terminology. So chemical plants and pulp and paper all often, if not, will mostly end up being ANSI systems. So a lot of the specs for the pumps end up kind of following that ANSI piece. At Swagelok, we've chosen to take the more conservative spec, which definitely ends up being the petroleum industry's API's version of the seal plans. And it's just that. Typically, they're much more conservative than ANSI, but there's still a lot of commonalities between the systems that they standardized on. And you would be surprised. Don't be surprised if you actually see a bunch of those commonalities even as you inspect the specs. It's even convenient for us because for the most part, API and ANSI has the same numbering system. It's just ANSI put 73 in front of the system number. So when I call it a Plan 52, it's actually a 7352 in the ANSI world. But the designs I'm going to show you for the 4 that I've typically seen in water systems, these are very, very common systems, whether we're talking ANSI or API. The one nice thing that API especially did is they really recognize the ability of tubing to hold up in high vibration systems over especially pipe systems. And they don't typically recommend hose because, again, with these systems, if you're trying to achieve 5 to 7 years, we know that hoses will typically have a change out period well before that 5-year period. So they strongly recommend either rigid piping these systems. And when you go from a rigid piping standpoint, tubing holds up much better in these high vibration systems around the pumps than even MPT pipe or really socket weld pipe would in most cases. They also made a handful of other changes that you can kind of see on here. For the most part, a lot of that I don't see as requirements in pulp and paper, especially. So the main plans that I've seen out in the field with these water systems end up kind of boiling down to the 4 plans. For the water type plans, you end up with your flush plans. We have an external flush, which I would say probably covers 80% of the plans that I see out there. And I've also had a handful of pressurized barrier fluid seal pot type applications due to the process pressures and or what is available for plant water system. And then in a few rare cases, I've definitely ran into some on gas seals. And gas seals typically are kind of a love-hate for any plant personnel. Those that really like them have a tendency to use them everywhere. If you've had a bad experience, it's kind of like anything else. You typically will avoid them because they do have a few unique features, as you'll see. So when we look at the flush plan 11, these are very, very simple type plans in that we're just taking our pump discharge, so our high pressure side, and we're actually just flooding it back into the system. Really, the whole point of this is to cool and lubricate this because, again, we have just a small trickle that's going through there that's 2 thousandths thick. And effectively what ends up happening is by the time it reaches the end, it's essentially evaporated. So we just have a little bit of evaporation that ends up going there. You should not see any visible drips. If you see visible drips, you're probably having either a wearing seal or the pressure is too high flowing back into this. And a lot of times they do put some type of throat bushing to really try to prevent fluid coming back into the seal. We really want to push new fluid in here. If you didn't have this tubing here, you can imagine all of this would just heat up to the point of evaporating, and then you would turn your liquid seal into a gas seal. and typically there's very special requirements for it to run on gas. So a lot of times then your pusher bearing would slam into the body bearing, and you would end up with a failed seal probably within 2, 3, 4 minutes. So the main considerations here is the pressure. The seal chamber must be maintained at a higher pressure than what the impeller fluid is, so that we get that nice circular motion, which you will almost always achieve as long as you're pulling from the downstream side. And you can see that if we get too little flow, the seal will get excessively hot and wear. And too much flow can definitely cause an excessive leak path across the pump, more so because we're causing that pressure to increase. One nice piece with the literature that we have set up for this is we give you kind of a good feel for this is what is required in the seal, this is what's optional. So what is required in a Plan 11 is what you see in the black. It can be literally as simple as taking off my discharge line and running it back into my seal. There are some different accessories that you can put in. You may require temperature indication, pressure indication. If you're following API, you're going to have a block and bleed off of that. And then depending on how much fluid you really want to be running back and bypassing through the pump, most people would choose to put an orifice in there. For the most part, mechanical seal companies have landed on a 0.125 orifice or 1/8 inch orifice for this, so that you're not bypassing so much fluid and losing efficiency on your pump. This is the simplest. This works really, really well for clean materials. You can imagine if there's any particles in the system, those particles then get injected into our seal face. And again, solids are typically a very, very poor thing that we want to. So that's where the external flush comes in. So essentially what we're doing is if we're pumping some type of slurry and or very dirty fluids, the last thing we want to take that dirty fluid and put it into our seal face that could potentially prematurely wear, or worse yet, plug around our seal face. So in a lot of especially pulp and paper type applications, what we'd rather do is we'd rather put in fresh, clean, and cool water into this. The big thing to kind of keep in mind with external flushes is because I'm taking water and I'm actually dumping clean water into here, I want to also push my debris and keep my debris in here. More than likely, you're going to be pushing any of your external flush. Now you're going to try to minimize that as much as possible, but you have to make the assumption it's going to go into my pump material. So that process fluid has to be compatible with what's going into. As long as this is a water-based process, it probably is not a big deal that I'm putting excess water into the system. Now, I again want to minimize that because downstream, eventually that water probably has to come out in some way, and there will be additional costs with having to remove that excess water that wouldn't have been there elsewhere. And in a lot of cases, I mean, we're talking hundreds of pumps. So if each pump ends up putting an extra gallon per minute of water into my pump system, those costs can add up very, very quickly. And again, you'll kind of see in a lot of pump material, this ends up being a very, very typical application. When we end up looking at kind of some of the main considerations, again, the fluid from the external really needs to be higher than our impeller fluid. Otherwise, we would actually have backflowing through there. And worst case, our pump material can come in and ruin our seal. It's extremely important that the media is compatible with the system. If you end up mixing something that's not compatible in there, you'll definitely have issues downstream. And we also, just like with the Plan 11, we want to make sure that it's clean and cool, mostly because if it's not cool, eventually we can evaporate out that liquid. The flows end up being very similar. Too little flow will cause the seal to get excessively hot and also allow abrasives into that seal face, and too much flow, the external flush fluid can potentially go into the pump, and ultimately it will increase your processing costs. Typically, you'll see these on external panels, or I've even seen where it's literally just the water plant spout hose and then hose running to a check valve into the seal. Our concept is to try to give you a little bit more control and really be able to set that flow rate. So at a very minimum, we would recommend that you have some type of flow controller. And talking to most of these guys, it's very important to have a check valve so you don't have potentially any of that pump material get back into the water system. And ideally, you'd have some type of shut off. Because it's so crucial that the material is clean, we also would recommend having some type of filter in there, and then you can get into, well, how do I know my filter is plugged, some type of differential pressure, and then also some type of bypass system that can go along with it. It's also good to know what my temperature is, and again, kind of my pressure set point. We've taken all this feedback. This is a very typical application out in petroleum industry. And at Swedlock, Minnesota, we kind of boiled down to what are the things that you absolutely need to have. When you look at just our basic panel mount front, we have our very simple flow meter, and we end up actually using our plug valves to be able to shut off and or bypass around that, especially if you have really dirty water and need to clean out your flow meter every once in a while, and then some type of flow control valve. One thing that we really try to incorporate on the panel mount version is we can set a green line for plant operations. We were getting a lot of feedback that this is great for the person that installs it, but it's really hard for people to walk by and know exactly what that pump requires. In most cases, I've heard anywhere from 0.3 to 0.5 gallons per minute. So what we decided to do is we set up a green line where any plant personnel can walk by, know that that float needs to be in the green. If it's in the red, why is it in the red? Is it somebody turned it down? Or especially if the flow is rising, that would be an indication that your seal is starting to fail if you're not already starting to see leakage out of the seal. And again, some type bypass. In some cases, we've even seen the pressurized barrier fluid seal pots. The big thing that I want to make note of is this is for an entirely different seal system. In most cases, we've been talking about a single seal. In this case, it would actually be a dual seal arrangement. So you end up with your process seal here, and ideally we want to push actually water across that dual seal. And again, because of how fine flow that goes across those seal faces, you essentially end up putting very little water into the process, though because I am putting water eventually into that process, again, and this does mediate does have to be compatible with it. And then on the other side, I actually have another seal that is seeing the cool fluid flow, and then that would be evaporating off. So the dual seal arrangement ends up being a very, very nice cost saving because you don't end up going through nearly the amount of water. Those that I've talked to where you're setting the Plan 32 at about 3 to 0.5 gallons per minute, this 5-gallon tank may only fill itself once or twice a week. So you can see that your operating cost of the fluid ends up going down tremendously. The other big piece with this is typically there is going to be some type of cooling water cost because again, I have to make sure that I'm getting cooling not just to one seal now, but to all both seals. And there's also some special considerations with making sure that I get enough motive force through here that you'll see. Kind of zooming in a little bit, once you get into more severe applications, you may even find yourself where you're using some type of seal flush type application here and making sure that you keep this face as clean as possible. If there is a failure there, then you can run into this dual seal type application. So then this runs essentially between the seals. This typically is a very corrosive acid that you would end up adding the Plan 32 out in the pulp and paper, chemical, food processing industries. I would say that you almost never would see this Plan 32, and it's more than likely plugged because it's sufficient just to run a small fluid film across this. It's not detrimental to the seal to have particles in this area if they do exist. And again, note that you have 2 seal faces. So the main considerations with the pressurized barrier fluid is really does come down to pressure. It's the fluid from the seal pot, again, has to be higher than the seal that goes to process, because I have to push my process fluid across into the process. Typically the numbers I hear is it has to be about 15-20 psi, anywhere from 15 to 25 psi higher than my process pressures, which in water, and especially pulp and paper, food industry, I've seen where typically most of these pumps are running anywhere in the 30 to 40 psi. As long as you have water service that's in the 55-60 psi range, more than likely you won't need that additional nitrogen or air pressure on the system, because the natural water pressure will keep it above. And then again, because the media ends up going into the seal, I have to make sure it's compatible, and the flow, I have to have fluid movement between the seal pot and seal chamber. So when we look at this type of seal arrangement, we sell the assembly, and then we also sell kits to run from the seal pot to the pump system. So we kind of really end up breaking it into 2 sections. Again, with water seals, as long as you have water pressure that's about 20-25 psi above what my pump pressure is going through my pipeline or from my pump output here, then I probably don't need this additional section here. And even this fluid fill line a lot of times can be run through a regulator and automatic fill system with this seal pot. So there are some different setups that you can do with water seals. You can get really crazy with some of the accessories and things that these can be highly customized for whatever application, and in a lot of cases minimized. The one thing I really want to focus on is, again, there's some special considerations with the pumping lines here. Because the pump doesn't have, they try to put a pumping ring in there, but even that pumping ring doesn't give you a lot of differential pressure from your inlet to outlet side. So a lot of times you're banking off of the thermal siphoning effect. So what ends up happening is, as the fluid warms up in here, hot fluids rise and cold fluids drop. So with the cooling coil in here that you would typically have, the cold liquid will get forced through here, and then as it warms up, it gets forced up through this. As you can imagine, there's not a whole lot of pressure there. So you want to minimize pressure drops between the seal pot and the pump as much as possible. Typically, there's a lot of standards around how far away you can go from that before you're going to have issues. From our perspective, the biggest issue is you want to use large radius bends. So typically that's 3 times the diameter that we end up actually typically seeing with these tubing systems. Again, it really relies on the thermal siphoning effect, and don't assume the pumping ring is going to be enough. So ideally, either small, short 45-degree bends or large radius bends. The worst thing you can do is put in pipe elbows. Because pipe elbows, there's a very, very big pressure drop when we're talking these fine of inches of water type pressures. Quickly, because I've seen a few of the gas plans, really the big difference is you end up with this dual seal arrangement. Again, these seals are very, very different in concept and grooving of how they do. I mean, you can even see in this picture how much wider those seal faces end up getting, but it's still the same. I want to put a small stream of gas across that. I want to be able to cool it, and I also want to limit how much leakage I have into my process. There's technically 2 different versions where I can let the liquid pass through this. The only ones I've seen is in pulp and paper, especially, is where you're actually pushing the gas and you're bubbling either air or nitrogen into the system. it needs to be a low amount because again, that has to be eventually taken out. But that may be an easier sell than adding some other type of additional liquid. So again, it's used with dual seal systems, and I have to have a really nice, typically nitrogen or air. Again, the nitrogen air, it really needs to be higher than the impeller fluid so that I'm pushing pressure into the pump on the Plan 74. And the gas really needs to be very, very clean and typically very, very dry. You can imagine any liquids will cause the same effect as solids do in the other plans. Liquids can have a tearing effect to these gas seals. And that's typically where people end up having problems. They don't have very clean or dry nitrogen and or air in their systems. And then the flow, you're trying to control what you're dumping into the system while also giving the seal what it needs. These gas systems, the panels themselves end up looking very, very simple. A lot of times we would recommend having some type of coalescing filter so that you're knocking out as much moisture as possible. Obviously need some kind of pressure set point. And then we found that even a rough flow control is not quite sufficient. Typically we do a rough and a fine to really be able to lock in that flow measurement. Everything else ends up being some type of bypass system, or especially if you're running multiples, it's very, very easy to all of a sudden have multiple gas streams systems in the system. That pretty much sums up the flush API Plan 11, the external flush, the pressurized barrier fluid seal pots, and the barrier gas. Of course, there's about 30 more plans that you can have out there, all the way going up to a very, very complex system like this. So far, I don't see any questions. If you do have any questions, feel free to enter them now. The only other thing that I was planning on kind of going through, like I did last time, is going through our mechanical seal literature. When you look at the mechanical seal literature, you end up with the application type guide. Again, we try to lay it out, kind of what is the system, a little bit of in-depth, and then when you get into the seal plans, you really get, again, that same look of, in red, you have kind of the secondary stuff, in black, you have some of your required components, and they go through every possible plan. The one thing that I don't want to give the impression of is if you do have any kind of questions, can't identify your pump supplier, can't even tell you what the plan is, feel free to contact me or your salesperson. It's usually, especially in these simpler plans, very, very easy to identify kind of what it is. And I can guarantee you that there's at least one or two things that we can help you with. And then you break down into these more complex, you do get kit numbers and you do get the assembly part numbers. So I am not seeing any questions. Again, feel free to reach out to your salesperson and or myself if you do have any questions. Otherwise, with that, I'll kind of hang on for the next minute or two. If I see anything, again, thank you for your time, and definitely let us know when you come up with any questions. Thanks, guys.